Thank you, Stéphane, for this interesting overview of the interaction between the long wavelength elastic waves and the civil engineering structures. Many examples of large-scale experiments. So please, people, if you have questions for Stéphane, you have just to switch on your microphone and ask your questions. You are not in the full screen anymore, Stéphane. Maybe you can put it back, your slides, or as you wish. So okay, I will start. I saw in one of your last slides, and I know that you are interested on this subject of the behavior of the elasticity of Rayleigh waves. Maybe you can explain a little bit more, first of all, how we can change the polarization of the Rayleigh waves with the help of the metamaterials, and also you can describe a bit the effect of the vertical and the horizontal component, the difference between, and the effect that can have on the structures.
Oh, yes, Bogdan, the concept is to say that most of the time we have to transform the soil by quite huge densification, but for an homogeneous soil, the densification could be so important that the first meter of the soil can change. So we are going from an homogeneous to a two-layer model, and the layering is a condition to transform to create the dispersion of Rayleigh waves. So we can explore theoretically the effect of the modification of the homogeneous to a two-layer model, the effect of the dominant displacement, horizontal or vertical. So a way to represent this in the frequency domain is to say what is the dominant amplitude in spectral domain of horizontal or vertical. So this is the representation in the bottom. We can see that for two layers, it's much more complicated for a multi-layer model, obviously. We can see that transforming an homogeneous to a two-layer, we introduce the dispersion wave. So the dispersion wave is also interesting because for some very specific frequency, we attenuate the horizontal displacement, and the vertical one is dominant. Vertical one is dominant, is much less deleterious than the horizontal displacement. I'm not sure I'm very clear in my explication. I apologize, but this is the concept to say we could have a consequence on transforming a soil, but we can also use this to modify a property, the dynamic response for the Rayleigh wave. Most of the time, we are designing with the shear waves. We are not still designing with the effect of specific effect of Rayleigh waves in earthquake engineering. So we have a lot of exploration to do for the complexity of the Rayleigh wave in this type of medium.
So if I'm not wrong, with these two layers, you're able to change the polarization also of the Rayleigh waves from the vertical component, from the vertical ellipticity to the, or you are more interested to change it the other way from the horizontal elasticity to a vertical one.
Yes, yes, yes. That's what we always doing when we do surface geophysics. Surface geophysics based of an impact at the surface. So this impact is propagating in the soil, and we have receivers. And what we can observe is that according to the layering of the soil, you can have a strong dispersion effect. And we're trying to find this profile of soil by inversion method. But when we do the exercise coming from an homogeneous medium and transforming a little bit adding layer, you can see this. I can't say that it is easy to do. What I simply explaining that we have to take into account all the complexity of the wave when we have modified the medium. So this is not only a shear wave modification profile, it could be also the frequency dependence of the Rayleigh waves.
Okay, I see. Thanks. Some other questions?
I have one small question. May I ask, Stéphane?
Yes,
yeah.
Professor. Yes,
Yeah, so yeah, it was very nice presentation. I'm just curious, you are using this damping parameters, right, for this model that you have shown. So how do you choose those parameters in reality? I mean, those numbers, for example, in slide number 41 or so, I mean, there are some models that you have chosen, right? For, I don't remember the slide number, but
yes,
some damping model, some spring constants, right, for modeling the soil structure interaction.
yes, clearly, we are touching a serious difficulty to define the parameter. I try myself to identify to test at the surface several soil acting with a vibrating source, harmonic source, and trying to identify the damping effect thanks to experiment on the surface. So it's quite difficult in, as you know better than me, obviously, all the difficulty to define this parameter, because we know for the building that it could be from 2 or 5%, because we don't observe a lot of cycle of vibration. But for the soil, we have very small experiments, a few experiments that you can say, but we have to test the soil for all the frequency, as the damping ratio is frequency dependent too. I recognize that the study is only parametric.
Okay, so you're performing experiments to estimate those parameters, but I believe your experiments are at a small scale, right? You're taking a small, I mean to say, like, these parameters can be scale dependent also. I'm just curious. I know this is a very difficult thing. I'm also trying to see how to get these parameters, because suppose you take a constant for a small scale experiment, and let us say we put it for a large building. Will they have any correlation, or you feel they will be same? I mean, constant.
This is a true question. We have candidate a few weeks ago to a national project to explore specifically this question, because to extract the information is not so easy, even for experiment at the surface, because we have the geometrical attenuation, we have the effect of the attenuation, purely attenuation. So we realize we were scared to realize that we don't have a lot of information.
Oh yeah, I'm just curious. Thanks a lot. I just wanted to, I had this confusion. Thank you. Thanks.
Thank you very much.
Mhm.
So any other questions? If not, let's thanks Stéphane for this very inspiring talk and so many examples of experiments.
I've got one question.
Please, Sébastien.
Stéphane, could you go back on the transformational aspects?
Yes.
Yeah, in fact, what I mean is the part where you have this lovely, incoming wave from the ground.
Oh, yes, it's very simplified.
No, but it's really, I think it's really a great idea, because essentially what you're saying is that these layers, they act as some kind of bent waveguide. So you have,
yes, the pattern of the layer can contribute to a waveguide. Yes.
So yeah, no, but what I mean is that we could do some reverse engineering here, and starting from your layering, we could envisage what is the associated geometric transform. You see?
Yes.
And so, in fact, we could view this layering as some kind of transformed medium, approximation of a transformed medium, and we could associate to this a Jacobian, so a mapping, and we could consider that all your substrate is actually a homogeneous substrate which has been mapped onto this kind of transformed substrate to achieve this bend trajectory. Don't you think so?
Yes, you're right. You know, as explained, when the great difficulty of earthquake engineers and seismologists is to have a good accuracy of the definition of this model. Most of the time, they do the inverse concept. So they try to understand, thanks to data acquired at the surface, try to going back to the base of the sedimentary model to find something not so wrong. But you're right, because what is interesting for few data on world is to have the information at the base of the column and the information at the surface. So you have the experimental transfer function for this situation. So it is very interesting to use this. And one of the concepts is not to have the pattern exactly, but to have the dynamic response due to this information. I understand what we are dealing with. Your concept is to say, maybe I'm not in the obligation to have all the information, but have only the global information at the surface.
And to view this with a different angle, so we could interpret this in terms of transformation optics. We say that here, because clearly your wave trajectory is bent, so yeah, we can say that even your transfer function could be associated with some kind of Jacobian. I mean, I think that it's really striking when you have the animation, you have this kind of animation that somehow it's really acting as a bent waveguide.
Yes, it's quite simplified. And one of the difficulty, as I presented for the duress of quake, so you don't have so simple effect. You can have a strong trapping effect, 2D or 3D effect at the edges of the basin. For the example of the earthquake in Albania, we are thinking that the geometry of the basin can create a concentration of energy in the edges. So maybe the concentration of damages could be induced not only by a simplified 1D model, but all these aspects. This is a great and still going challenge, because I think that earthquake engineers are able to really design with quite a great accuracy the structure if they have all the elements. But the unknown parts of this is all the complex effects due to the geology in specific situation. You know, earthquake engineers had a very approved science, so they can design very in the finest way. But the modification of the signal, even in small thickness of soil, could create a lot of effects. So sometimes not so easy to identify. We have to measure. You know, I'm a candidate to say measure, continue to measure the effects of the surface, because we can't have a global effect, but very specific information. We have to develop and to measure.
May I say something? May I interfere a little bit?
Excuse me, Professor Gazetas.
Yes, can I say something just on this picture? Now, even with horizontal layers, purely horizontal layers, we will still have the bending of the curve upward. It's the Snell's law of refraction, going from stiffer to softer soils.
Yes.
The additional thing that the inclined layers will do is that they will create Rayleigh waves, or SH love waves, depending on the situation, at the edges, at the very edges, as I think Stéphane mentioned already.
Yes, you're right.
That's a big
Yes. The complexity is still there. The complexity is still there. We are still a little bit humble to
Yes.
this effect. So what demonstrates the metamaterial is to say, for a complex geology too, not only for the transformation of the soil at the surface, we have already a great complexity. So
you're very right, very true.
So I think.
Thank you for your presentation.
Yes. All people doing a lot of experiment at the surface, I think they are in the right direction, because they can understand a lot of effects. So we have to still measure to identify all the effects. It's not so easy to extract because the amplification is the same for the building, the frequency of the building is the same as for the soil sometimes, and so we have to observe finest element, finest effect inside the soil. The structuration of the soil is not so easy to extract them.
And so whenever you have the interface between two layers, of course, you have coupling between in-plane pressure and the shear.
Yeah.
And so even if you start only with a pressure wave, necessarily, as soon as you have an interface,
you generate those waves.
Shear and pressure, it's fully coupled, your problem.
Yes. It's quite difficult to have a full wave propagation modelization, but this is a way to resolve this problem. But as said Professor Gazetas, we have also difficulty of the pattern. So the pattern is very had a great influence on the result.
And in fact, do you think also that you will have a coupling between anti-plane shear and in-plane waves? I mean, let us imagine that your incident wave is purely in plane. When you reach an interface, it will remain in plane, or you will have a coupling between out of plane and in plane?
As long as the layers continue in the horizontal direction without changing, of course, they will remain in plane. They will remain in plane. there's no reason to create out of plane. There's no shear or normal force acting in that direction, so they're not generated. I'm sorry, I answered instead of Stéphane.
And Stéphane,
sorry, Stéphane.
Oh, no more. That's right. See, the simply incidents, vertical incidents, are limiting the modification, the conversion of wave at the interface. We have some small situations that are limiting the cases, but basin are except in the huge basin, in the center part of the basin, we don't have exactly horizontal deposition of the sediment. Maybe at Mexico, maybe at the center part of the Mexico, maybe we are reaching a little bit this perfect model, maybe, but the basin himself is in a U shape at a huge size, but have very specific conditions that when the model is right, it can explain a lot of things. So yes. I recognize that we can make this first assumption is quite good for explain a lot of evidence at the surface. That's right.
And do you have some creeping waves, some waves at the interface between the layers, you know, that propagates along the layer?
Yes, we have, according to the contrast of velocity between them, we can have in seismology, this is a refraction for exploration, for seismic exploration, and have a reflection on evanescent wave at the interface going to the surface, but it's very quickly evanescent. It's quickly evanescent in certain conditions. We have this, but the frequency content of an earthquake signal is not harmonic. It's plane of frequency from a range. So we have all simultaneously all the phenomenon in each time.
And what do you expect for the building, which is just, you know, above your incoming, you know, ray? What's going to happen for this building?
Well, in this specific example, we have the maximum horizontal displacement in use, but it's not necessarily a problem. Because if you know, if engineers have the good information for the displacement of according to the time for the design, we are absolutely able to perfectly create a resisting element. This is the case of the Mexico City, because Mexico City, it was very a destructive earthquake in 1985. But the municipality of Mexico had absolutely correct the elastic spectrum, the design spectrum for all the elements. And sometimes you can confirm, Professor Gazetas, sometimes 2 times the initial value than 30 years ago. So they had the good behavior of the building if you have the good acceleration to put inside the model. So, actually, the method of sizing of design is quite performant.
But in this case, if you have the wave which is incoming vertically, is it useful to have this kind of pendulum at the top of the building?
Yes, exactly. It's quite be efficient for this, for the wind, or sometime for the earthquake. It is 5% of the mass of the building. It could be interesting, but you know, this is the pendulum, the turn mass damper is very interesting for the comfort. Sometimes for people inside, because we are limiting the displacement. The building is resistant for the earthquake reference earthquake, but sometimes we have a too important drift the displacement between two floors. So it can create a bad feeling inside the building. So sometimes the tuned mass damper is also used for the feeling inside, the seasick. Not only, but it can be to reduce the displacement for the building.
And in this case, again, may I ask some naive question here? Is it better to have some very stiff foundation or to alternate, stiff and hard medium, like rubber and concrete, just below the building? What would be the most efficient when you have this kind of incoming signal? What would be the kind of anti-seismic design, just, intuitively?
Intuitively, this is very efficient to create something that give an increase of the equivalence period, something apparently more flexible. Most of the time it is better, but the balance is the economy. So we are not. We try to do this type of insulation only for huge projects with consequence in case of collapse. This is hospital or nuclear plants because we have to take a so important horizontal loading that we're not able to easy design the concrete for this. So at the moment, it's better to put insulator at the basement than trying to have huge concrete section. This is economical balance. It's an economical balance.
You mean also soil pollution, no?
Soil pollution, not exactly. So here this is only the mechanical effect. But it's a mechanical effect. Instinctively, we have to have a flexibility of the building. That's good. But the price to pay is the displacement. In Mexico City for the 2017 earthquake, we have a great. The displacement was very important between two close buildings. So we have the shocking effect between them. Tens of 20 examples like this. So we can.
So you mean just a minute? I'm a bit lost. You mean buildings interact with each other? This is what you have in mind?
Yes, but they interact. They are shocking each other during the earthquake. If we accept flexibility for the building, it's good for the equivalent horizontal force applied to the building. But the pay to price is that flexibility is more displacement at the top of the building. So that flexibility is good, but we have to introduce the amplitude of the displacement.
So you mean you should space more the buildings that should be further apart? I'm not sure I understand.
No. You have to strictly design the amplitude, the relative displacement between two buildings with two different fundamental periods. Because we have two different fundamental periods on two different approach on flexibility. Their relative displacement could be a problem because they can shock each other. You have to let a space between the two buildings. Is permitting to don't have a shocking effect between the two buildings because two buildings are not necessarily in phase. There's a shift phase between them. So if they have a shift phase in phase, they can shock each other.
So you mean they are anti-phase and they would collapse on one another?
Yes. A tall one on a small one.
For instance.
And at the Mexico City,
for instance, in your configuration, the tower might interact with a small building in the middle?
Yes, they interact mechanically by the displacement at the surface, but they interact obviously in a secondary seismic source.
Yeah, and so which is the building which is the safest? It's a small one, no? Not necessarily.
Not only because if we are this small building in a small thickness of soil,
yeah,
it could be in phase for the resonance effect, because the frequency of the last soil here could be the same than the small one. So it could be in resonance due to the effect.
Okay.
So this huge building is not in a well position, because the soil here is thick and maybe the soil is soft too. So it could have the same frequency, fundamental frequency, than the soil.
Okay.
If the basin is thick, you don't have a tall building.
Yeah. And so here, do you consider that the basin is just the green area, or it's all the layering? What is the basin here?
Oh, here the basin here is a yellow one. It's coming from number 4 surface, for example, because here we have an incident. You can consider that this is the seismic substratum.
Yeah.
Seismic basement. So it's a rocky ground. So we are progressively going to soft soil to the surface.
Yeah.
So this is.
In fact, my question is, what is the fundamental frequency of this basin? The fundamental frequency is given by the very large yellow area, not only by the green.
We can observe 2 frequencies. If the first one is very soft, under a more stiffer but not rocky ground, we can observe at the surface, by means of H/V technique, can see 2 peaks of frequency, demonstrating that the first layer has its proper frequency, and we have the information for the deep basin to the rock. If the velocity is going regularly to the depth, there's only a frequency. But if the first soil is very soft and the soil number 2, number 3, number 4 is stiffer but not rocky, we can observe a specific frequency for all the parts of the basin.
Thank you so much. I'm sorry for the very elementary questions I asked, but I think, you know, this slide is really formidable. I think there is a lot of the physics that I understand, which is in this slide. I think this slide is an excellent.
I realized this to improve the understanding, because when you are speaking about wave incoming in the basins, that's a story of specialists. So this is a way to reproduce exactly what we do for the design. For the design, we take into account this plane wave incoming at the basement that we are exactly doing.
And this is also in line with what Professor Gazetta said a few minutes ago. You confirm that in most cases, whichever is the incidence, when the wave will hit the surface, it will hit the surface at normal incidence. It will become more and more vertical.
Yes.
Always.
Not always. This is a dominant effect, because the condition is that the epicenter is quite far from the place.
Yeah.
So the waves are propagating inside the earth, but each layer of earth are going stiffer to the center of the earth. So this is the effect, the inverse of the effect. The vertical ray is going more and more with a huge angle. And
Ah,
at
yeah,
the moment,
okay.
at the moment, we have the opposite effect. So the wave is going to the surface before going to the depth. You know, you have an inversion because we have a total refraction at the depth.
So,
absolutely the same as optics.
yeah, and I have another elementary question. So this is one scenario which is very important, but of course you have the other scenario when you have a Rayleigh wave on the surface.
Yes.
And so which of these two is the most destructive?
In the common theory, the Rayleigh waves are very destructive because we are propagating at the surface, but we are speaking about not in-use Rayleigh waves inside the basin due to the coupling effect of compressional wave on vertical component of the shear waves. But we are dealing, when we are speaking about this type of strong Rayleigh wave, we are speaking about teleseismic earthquake. You know, the wave is propagating from the epicenter to another point at the surface. It's much more energetic, but we are dealing with long wavelength for the Rayleigh waves. We are not speaking about the same type of signal. Here for the basin, we are dealing with Rayleigh waves in use in the basin.
Okay. Thank you so much for answering my.
Thank you for us. Thank you for.
It's fantastic. I really love this slide, I must say.
If I can, what I find very interesting on the slide is that allows us to imagine that we could obtain an equivalent of the rainbow effect on the vertical vertical rainbow effect due to this change of layers properties on density and other stuff. That could be very interesting to see if we could
yes, you're right
control the propagation of the bulk elastic waves on this direction due to this effect, to the rainbow effect.
Yes, you're right. That's right.
Very nice, very interesting.
It's a great idea. I mean, no. It's absolutely. So what you say for people, Bogdan, is that since your layers have a different thickness and it's a graded metamaterial,
yes, graded.
You should be able to stop the incoming wave at some point. This is what you mean, Bogdan, no?
Yeah. It could be
or segregate the frequencies.
Can get, or different polarization, or I don't know, part of the wave, the bulk propagating to this medium.
So what you say is that, in fact, Stéphane should replace his animation by a rainbow, the same kind of thing, but the colors should change.
Even kind of a filter of
yes, a filter. Yes, a filter.
On the vertical, I mean.
And what is very interesting in this approach that we have only to take into account the effect of the filter. For the user, it's very simple. It's just using a transfer function with all the complexity of the rainbow effect, for example. And this is only an input to plug inside the model. This is the implementation. As we see, I do exactly this figure because, you know, I have reduced the wavelength at the surface. You know, I took a long time to realize this animation.
That's right. I missed it, but Bogdan completely got it. What you show us, it's so exciting because you show us a rainbow. That's right. No, that's right. This is exactly the rainbow. Now thinking,
yes, you're right. That
yeah.
theoretically, it's exact.
Yeah. Wow. Yeah.
Oh, thank you.
Okay,
Thank you very much for the discussion.
Thanks again, Stéphane. Thanks, everyone.
You're welcome.
See you next week when we have Moti Segev from Israel Institute of Technology, and Moti will speak about the topological photonics. So see you then, and stay safe.
Thank you very
Bye-bye.
much. Bye-bye.